All right, welcome back, everybody. Hopefully, you had a nice and restful spring break. At least got some time where you didn't have to do any schoolwork and you could just kind of um, take a break, maybe hopefully get outside and do a few things, go for a walk or whatever. We can't do a whole lot right now, but at least you didn't have to do schoolwork. I'm kind of sad that I won't get to see you guys at all for the rest of this school year, but I am looking forward to the fall when everybody comes back. Um, You'll all be in geometry or pre-cal next semester. So I look forward to seeing you guys all then, and hopefully we can still get through this last few weeks um, covering what we can. We're going to keep it pretty basic, but we want to hit the important things that you'll need for later on in your math career or stuff on the SAT and such. So before break, we were talking a lot about infinite sequences, just about sequences and series. We're going to do one last little topic on that today on infinite series, and then we'll do some review in our next class. And then our third class next week, we will have our assessment over this unit. It'll be a take-home assessment, and I'll give you some more details on that when we get closer to it. Okay, so infinite series today. One other thing I want to make sure I clarify is last week when I graded your quiz twos, I had a lot of people, I wasn't 100% sure that we understood that there is a difference between the word sequence and the word series. So those are two different things. If it's a sequence, then I'm just writing the numbers 2, 5, 7, 9, 11 with commas. If it's a series, I am adding all of those numbers in that sequence. So 2 plus 5, plus 7, plus 9, plus 11. So you may notice that correction on your quiz. Make sure you know the difference between those two things. That's important. Okay, so series is when we add them all together. We had some formulas for arithmetic and geometric sequences in series last couple weeks. We're going to look today at an infinite series. So again, we're adding up terms, but this time, if it's an infinite series, that means it goes on forever. Right? We don't have a stopping point where the sum stops. So first one we've got here is 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and it's going to, that dot, dot, dot just means that it's going to keep going on forever. There's no ending point at all. So it's kind of weird to think, like, how do I add up all of those terms if it never ends? Well, let's see what happens. So first thing we always need to do if I'm going to find the sum of a series is to figure out if this is arithmetic or geometric. So if I look at going from 1/2 to 1/4, well, I could I could subtract 1/4, but then if I do 1/4 minus 1/4, that does not get me 1/8. So let's try this again. If I do 1/2 times 1/2, oops, sorry, got off there. If I do 1/2 times 1/2, that gives me 1/4. If I do 1/4 times 1/2, I get 1/8. 1/8 times 1/2, I get 1/16, right? So this is a geometric series. And we've got an R value. Remember, that's our common ratio. I'll write it out here so we remember. So our common ratio, or R, would be 1/2, because that's what we are multiplying by each time to get the next term, right? Okay, so then if we remember our formula for the sum of a geometric series, our formula was to take the first term, so a sub 1, and then do times 1 minus the common ratio to the nth power, all over 1 minus the common ratio. And remember that n is the number of terms that we're adding up, right? Okay, so let's plug in our stuff here. So if we want to find the sum, now the question is, how many terms are we adding up? Well, an infinite number of terms, right? So we're finding an infinite sum. So there's an infinite number of terms. I'm going to write my little infinity symbol there. And I would take my first term, which is 1/2, and then I'm going to do 1 minus my common ratio, which is 1/2, to the nth power. And again, the number of terms I'm adding up, it's infinite. So 1/2 to the infinite power, and then all over 1 minus 1/2. Okay, now again, this is kind of weird, because if I'm thinking 1/2 to the infinite power, like, how do I calculate that? So let's think about that over here. If I do 1/2 to the first power, that gives me 1/2, right? If I do 1/2 to the second power, That'd be 1/2 times 1/2. So that is 1/4. Okay, how about 1/2 to the third power? Well, that's 1/2 times 1/2 times 1/2. That's 1/8. And I can kind of keep going with this idea just to kind of think about what's going to happen if that number, 1, 2, 3, 4, if I keep getting bigger and bigger, right? So next would be 1/16. I could do, let's skip a few. We'll do 1/2 to the 10th power. I get 1 over 1,024. So if I look at these numbers over here to the side, right, 1/2, 1/4, 1/8, 1/16, 1 over 1024. Notice the top number is staying 1, but the bottom number keeps getting bigger. So remember, a fraction is division. So if I keep doing 1 divided by 2, let's even kind of write these here. That's 0.5, right? 1 divided by 4, that's 0.25. 1 divided by 8, I believe that is 0.125. Oops, 125. 1/16, that is 0.0625. And if you want to go bigger here, 1 divided by 1,024, that is 0.00098, right? So if you look at these numbers, they're getting smaller and smaller and smaller. And the bigger that this bottom number gets, the smaller that this decimal is going to get. And if I went to like 1/2 to the like 1,000,000th power, I'm going to have a whole lot of zeros after that decimal point. So this fraction, as I do 1/2 to the 10th power, to the 100th, to the 1,000,000th power, as that gets bigger and bigger, this number, this 1/2 to the infinity, is going to get closer and closer to a zero, right? So really what we're looking at here is the sum of our infinite terms. We're starting with our first term, 1/2, and then that 1/2 to the infinity power is really like 1 minus 0, because 1/2 times itself an infinite number of times is going to get so small that it's going to be like it's a 0. Okay, so then if I think about that, 1 minus 0, that is just 1, right? And 1/2 times 1, that's just 1/2. So that 1 minus 0 part just kind of goes away. And then on the bottom, 1 minus 1/2 is 1/2. So I get 1/2 divided by 1/2. We end up with that sum is 1, right? And if you kind of think about this, you're taking a half and then adding half of a half, which is a fourth, adding half of a fourth, which is an eighth, adding half of an eighth, which is a 16th. If I keep adding a half, I'm eventually going to get to a whole, right? I think I've shown this example in class before. Like if I'm standing here, right, and I want to end up over here, and I walk half of that distance, well, now I'm here. And then if I go half of that distance left over, and then if I go half of that distance, and so on and so forth, right? Now, eventually, theoretically, if I keep having that, I'm really never ever going to make it here. But in practice, I'm eventually going to be right on top of that dot if I keep going halfway. So think of like this is 1/2, this is a fourth, right? And if I add all those together, I get that sum of 1. Right? So sometimes an infinite series does have a sum, right? This is called a series, or an infinite series that does have a sum. It actually is called a convergence, or it converges, meaning that it converges to this value of 1. Okay, so that infinite series did have a sum. All right, let's look at our next one. This one is 1 plus 10 plus 100 plus 1,000 plus 10,000. So again, I'm going to look at this as this arithmetic or geometric. This one seems pretty obvious. I'm going to multiply by 10 every time, right? So again, this is geometric. And this time our R value is 10. Okay, now if I think about this one kind of like the last time, right? 1 plus 10, that's 11, plus 100, that's 111, plus 1,000, that's 1,111, and so on and so forth. What's going to happen as I keep getting bigger, and if I add all of those up, that sum is just going to keep getting bigger and bigger, right? This one doesn't actually converge on a value. It just keeps getting bigger. So this sum, we can't evaluate. because the sum just keeps getting bigger, right? So sometimes if you've got the fraction kind of idea, you might end up with a sum that converges. This sum, actually called, it diverges. It goes away from a value. So it doesn't have a sum. So we would just say that this has no sum. Okay. Okay, so this formula that we did up here when we did our infinite sum, notice that that 1/2 to the infinity, that part just kind of went away. So there is a formula for an infinite geometric series. It does have to be geometric for this to work. That's the only ones that you'll see. Is that the sum is equal to the first term divided by 1 minus the common ratio. Notice it's very similar to our other geometric formula. We just take out that part where it's 1 minus r to the n because that part becomes just 1. So we end up with this formula here for our infinite geometric series. There is a catch though, and that catch is that our geometric series, our infinite, only has a sum if the absolute value of the common ratio is smaller than 1. So notice our common ratio for this first one was 1/2, right? That 1/2 is smaller than 1. Our common ratio for the second one is 10. That's bigger than 1. So it doesn't have a sum, right? So our common ratio has to be less than 1. Okay, so let's try a few more examples thinking about that and using our formula. See if we can do these a little bit quicker this time. Okay, so we know it tells us right here that this is a geometric series. We want to find the sum. This dot, dot, dot over here tells us that these are infinite series, so they go on forever. So we've got our formula. We just have to be able to make sure that we have the right R value in order to use the formula, right? So we've got that our sum is going to be the first term divided by 1 minus the common ratio. But I can only use that if R is less than 1 or if it's bigger than -1. Because remember, we talked about the absolute value of R. So it can be a negative R, but it has to be between -1 and 1. Okay, so let's figure out what our R value is here, right? This one's not quite as obvious because it's not just a like ×2 or ×3. So that usually tells me that my R value is probably a fraction. One way to figure that out is just take the second term and divide it by the first term. So I'm going to do 18 divided by 27 to figure out what my R value is. And if I reduce that, those are both divisible by 9, right? So my R would equal 2/3. Okay, well, 2/3 is less than 1 and it's greater than -1. So that means this one works. We do have a sum. That means this converges. So we can use the formula, right? Okay, so then to find our sum, I would do my first term, which is 27, divided by 1 minus the common ratio, which we just figured out is 2/3. Okay, so then I get 27. 1 minus 2/3 is 1/3. And remember, if I'm dividing by a fraction, that's the same as 27 times its reciprocal, which is 3/1. And 27 times 3 gives us a sum of 81. So our infinite sum there is 81. Okay, and you kind of think about like 27 plus 18 plus 12 plus 8. See how the numbers are getting smaller and smaller, right? So we're adding a smaller amount every time. These numbers aren't always going to be fractions that you're adding up, but your common ratio is probably going to be a fraction or a decimal in order to have an infinite sum. Okay, let's look at the next one. Again, we already know it's a geometric series, so we're looking at what are we multiplying by to get this next term, right? Our terms are getting smaller, so it does seem like maybe this would be an infinite series that has a converging sum. However, it kind of alternates this time. I've got a positive number and then a negative number, positive number, negative number. So let's see if that makes a difference. Okay, so our R value is what are we multiplying by to get from 24 to -12? Well, 12 is half of 24, so I would have to multiply by -1/2. To get from -12 to 6, that would work again if I multiply by -1/2, right? Okay, so that means our R value is -1/2. So I want to ask myself, -1/2 needs to be less than 1, which it is, and it's got to be greater than -1, which it is, right? So this is a converging sum. So now we can go use our formula. We do the first term divided by 1 minus the common ratio. So I'm going to do 24 over 1 minus, remember that minus is part of the formula, and then our common ratio is -1/2. Watch your signs there, be careful. So that would turn into 1 plus 1/2. That would become 24 over 1 plus 1/2 would be 1.5, which is 3/2. And again, remember, dividing by a fraction would be the same as multiplying by the reciprocal, so times 2/3. I can put my 24 over 1 and do a little reducing here. That's a 1 and an 8. So then we get a sum of just 8 times 2, which is 16. So there's our sum this time, right? And you can kind of think of like you're starting with 24, and half the time you're subtracting a number and half the time you're adding a number. So it does make sense that our sum is a little bit less than our first term because we're subtracting and adding kind of back and forth. All right, one more example here. Again, from the directions, we know it's a geometric series. We just need to look at that R value, right? So what am I doing? 2/3 times what would give me 1, right? So you can think about it like 2/3 times whatever our common ratio is should equal 1. So if it helps you to solve it that way, you can do it that way. Well, to get rid of the 2/3, I can multiply by 3/2. So that means our R would equal 1 times 3/2 is 3/2. There's our common ratio. And if I look at the next one, 1 times 3/2 would give me 3/2, right? Okay, so 3/2, well, that's 1.5. That is bigger than 1. So if our common ratio is bigger than 1, that is not a converging sum. That is a diverging sum, where it diverges. So this one has no sum, right? These numbers, as they go, are going to get bigger each time. And if those numbers are getting bigger every time, we're not going to have a sum that it gets closer and closer to. So there's no sum there. Okay. Okay, so infinite geometric series, we'll only talk about geometric. An infinite arithmetic series would always diverge because even if the numbers are getting smaller, we're still adding another number every time that makes the sum bigger. It doesn't diverge. Or, I'm sorry, it doesn't converge, so it'll always diverge. But anyways, these will always be geometric. You get the same formula. You just have to make sure that your R value is between +1 and -1. Okay? Okay, your homework today is going to actually be on Google Forms. We're going to try something a little bit different. Make sure you're doing the work on a separate sheet of paper, but then you just have to type in the answers. Read the directions carefully. They'll tell you how it works. Let me know if you have any questions, and I will see you guys in a couple days, or hit me up on Google Chat if you need some help. Thanks.